Hello, everyone. Welcome. Thanks for joining. Feel free to say hi in the chat, pop in, and let us know where you're joining us from today. Hey, welcome. Just waiting for a few more folks to come in, and then we'll start.
Corey, it looks like we have a very broad representation across the country. That's wonderful.
Yeah, that's great to see. And Emma or Jesse, I'll just wait for you to give me the verbal notification that we're ready to start.
Ready when you are.
Okay, great. We'll start. So yeah, welcome everyone. Super pleased to have you here. We have some excellent speakers for our GMF webinar series today. Some more coming in. Someone from Bridgewater, nice to meet you. I've worked a lot with the folks out east. Good to see you. I'm calling today from La Chute, Quebec, myself. So thanks for joining for this edition of the GMF webinar series. We host this series every month, and we'll feature different topics focused on different GMF programs, starting in June and finishing in August. This month's webinar series, we've been tackling subjects focused on reaching net zero GHG emissions. And today we're talking specifically about energy efficiency, thinking about the community building retrofit initiative specifically, and how you can reduce emissions in your public buildings. So if you're already receiving support from the CBR initiative, or if you're interested in it, feel free to pop a question in the chat, because we have a lot of helpful GMF staff on the call who can answer any of your questions. So my name's Corey. I'm an advisor at GMF with Green Municipal Fund's capacity development team. And like I said, I'm here with my colleagues who are really pleased to answer any of your questions throughout. And that includes store specialists talking about building envelopes today. Many years of experience from them, and they're happy to help you out. Before we go any further, I'd like to take a moment to do a land acknowledgement. On behalf of FCM, I'd like to begin the session by acknowledging that I'm joining you from the lands that have been inhabited by Indigenous peoples for thousands of years. We at FCM recognize the Algonquin and Anishinaabe people as their traditional custodians of the land upon which the FCM offices are located. We also recognize the contributions of Métis, Inuit, and all First Nations, both in shaping and strengthening this community and country as a whole. Wherever you are, please join me in paying our respects to the original stewards of this land and committing ourselves to thoughts and actions that will lead to meaningful reconciliation wherever we live now. I also encourage you to add wherever you're joining from. I see everyone's still adding in, but there's some new folks coming. So bienvenue and welcome. Before we dive into the topic du jour, I have a couple of housekeeping items. So today's event will take place in English with French interpretation. To join the French interpretation, you can click the interpretation globe at the bottom of your screen. You should see it there. We also have two separate slide decks in English and French. See the options at the top of the screen to switch between the two. So you can select the options arrow, you'll see the drop down, and you can select English ou Français, c'est ton préférence. And as we move through the presentation, I asked you to submit your questions in the Q&A box specifically, so we know how to filter them out, and we'll try to get back to you as soon as we can. And we have a time saved at the end for a Q&A session. So thanks and welcome. Today's agenda, we have two excellent speakers with decades of experience. Stephen Dixon, who I'm told And in my experience, needs no introduction, but we'll introduce him anyways. He's an energy expert at No Energy, and he's been working with GMF and focused on our energy savings programs for many years. Very pleased to have you back, Stephen. And Christian Flores, project manager at WSP. At the end of their sessions, we'll have a bit of Q&A, as I mentioned. So feel free to ask your questions then or throughout the time. A lot of you might know already what FCM's Green Municipal Fund is all about, but I'll give a very quick intro. So FCM is the Federation of Canadian Municipalities. We're the national voice of local governments and represent over 2,000 member municipalities in every part of Canada's 10 provinces and 3 territories. FCM's Green Municipal Fund helps local governments switch to sustainable practices faster. Our unique mix of funding, resources, and training gives municipalities the tools they need to build resiliency and create better lives for Canadians. GMF is a $1.6 billion program funded by the Government of Canada. And the part of that funding that we're thinking about today specifically is around the Community Buildings Retrofit Initiative. Feel free to check out our website and our learning center for more information on what we can do to help you with your community buildings increase their efficiency. With that, I'd like to pass the microphone over to the presenters today. I believe we're starting with Christian. And yes, over to you, Christian.
Okay, thank you, Corey.
You're welcome.
I think Stephen will actually start us off.
Exactly, I will. And thank you. And thank you, Christian, for coming along. And Corey, I'm going to go back to words you used in your introduction, energy expert. And I learned many years ago that an expert is the person that knows the limit of their knowledge. Whereas I've been an energy person for better part of 42 years, starting out from Prince Edward Island many, many years ago, I would not call myself a specific expert at building envelopes, hence why I've asked Christian Flores to come and join me today. So I'll be starting off the session this morning, and then I'm going to pass over to Christian, and he can take you through some of his expertise and some of his examples. And then I'll come back in and finish off towards the end, a little bit about some tools that you can use. So the objective for the session today, from your point of view, is that you can walk away being able to describe the mechanisms for heat loss through building envelopes. So, and we've designed this session for maybe a less than a more technical audience. So if you're not, heavily technical oriented, then we've tried to design the session for you. Again, so you'll be able to describe those mechanisms and talking about this with folks in your municipality. To be able to identify some of the tools and methods for assessing opportunities. And that specifically speaks to things like thermography, but also analytics and modeling, and I'll speak to that towards the end. And then we'll try to give you an idea of the scale and the scope of saving opportunities and what types of things you can be doing. Some of the things are going to be sort of, what might call them no-brainer or very quick things, and some of them are going to take a lot more effort, a lot more money, but are going to be necessary if we are going to get to our goals of reducing our impact in terms of carbon to net zero, ultimately, for many organizations. So an important part of it, but we do have to plan. And Christian will speak to that one quite heavily, as I will as well. Christian, we can move to the agenda very quickly. So what we'll cover off here in our agenda this morning, I'll let you get to the next slide there, is sort of some very basic ideas around heat transfer principles. We'll look at the building as a system. We want you to think about your building as a system, not just, I got to fix those windows, but what can I do in a much more holistic fashion? And certainly getting to net zero, we have to take this holistic approach. And as a result, there is an order. And I'll speak to that one, and Christian will speak to that one too. But basically, I have 3 words that I use. It's not written on a slide anywhere. Waste, energy we don't need to use. Efficiency, how well we convert the energy from the purchased or the acquired form to the end use form. And then supply, the use of renewables. So that says, before we put those solar panels or that renewable energy in, let's not waste energy, and let's be as efficient as we can. So it's important to understand our building as a system holistically, measuring and estimating the heat loss, right? Where's it all going, right? What are the largest consumers? And it may be surprising. Sometimes we think certain things are the larger consumers, but when we actually get down to it, they're not. We'll take a look at what the envelope opportunities are And then we'll finish off very quickly on RedScreen Expert as a tool. And I'm going to show you a tool that you can use. You'll be able to jump in tomorrow and actually play with this one if you choose to do that. So Christian, let's move over to slide on thermal energy basics, or thermal heat transfer basics. So for those that aren't technical, this slide will be a bit of introduction. For those that are technical, this is going to be like second nature. But there are fundamentally only 3 ways in which heat moves. In fact, there's only really 2 ways, and one is a sort of variation of the other way. So heat can be conducted between 2 bodies. We're all familiar with that. So we have to, in order to stem that flow of heat in the building envelope, we have to use an insulator. We're all familiar with that. But there's another very important form of heat transfer, and that is that a body can radiate. Stand near a stove, you feel the heat radiated. A lot of people think when they stand near a cold wall that there's a draft, but it's actually the heat radiating from your body to that wall, right? So those are very important mechanisms. Now, if you put a body in contact with, a hot body in contact with, let's say, air or a liquid, you'll end up with what's called natural convection, because as the liquid or air heats up in conduction with the body, it will rise, right? That's we know that. Or if we force liquid or air to come into contact with the body, it will transfer heat. So really that's a convection, what we call convection, whether it be natural or forced, is really just a variation on that theme of conduction. So those are the methods that heat, or the ways in which heat moves. Now, on the next slide, if we look at the building as a system, there are many, many ways that heat moves into and outside of a building. And certainly, again, we have to build an envelope. And the envelope really means a boundary, right? And we want to consider that boundary. And boundaries are very important in building envelope analysis. Christian will speak to that one. So I'm going to let Christian take over here, and he will sort of gauge his time through this, because there's a lot of topics to go through here. And not a lot of time, but basically what we want to do is think about how we can modify any of those heat flows out of, and maybe into a building, even including solar energy. Christian, over to you.
Thank you, Stephen. The only thing I'll add to this slide is thinking of the envelope as the skin of the building that separates the indoor from the outdoor environment helps us think about how we can actually improve the performance of the envelope. The envelope controls the heat loss by insulating materials and keeping things as airtight as possible. So when we look at retrofit projects, that's really what we're trying to focus on. So here you see a cross-section of a typical steel stud wall. With some insulation between studs. So when we talk about insulation, we often think of that fluffy pink stuff in our walls. That material's there just to slow down the amount of heat transfer through the wall, but that bad insulation is not continuous, right? There's steel studs stopping it every 16 inches or so. And this is a very conductive material that will allow heat to escape very easily to the outside if there's nothing to stop it. The other thing about the fundamental physics of heat transfer is that heat will take the path of least resistance, right? So when we have a very highly conductive material, heat will tend to go out through that material. We call this a thermal bridge. A simple way of dealing with it is by insulating the outside of the building, having exterior insulation. It's the idea of you want to wear your sweater versus eat your sweater. That is how we tend to deal with thermal bridging issues. Now, every material has some insulating value. This is called an R value. R stands for thermal resistance. So when we talk about the R value of a wall, we're including all the elements of the wall into that number. And as you can see here in this example, the R11 bad insulation is really doing the heavy lifting in terms of total R value. But one thing that this analysis doesn't take into account is that thermal bridging that we just talked about going through the studs. And we'll see how to account for that in a few slides. So there's different types of insulation. Insulation can come in different R values. Typically, the higher R value you use, the more expensive it is, but not always. There's other factors that go into what material you use, such as vapor permeance or durability, and so on. Sorry, skip this slide. The other main way that buildings lose heat is through air leakage. And The control of airflow through our buildings is very key for several reasons, not just for energy loss, but also to improve thermal comfort for your occupants. Preventing condensation within the assemblies is a significant durability issue that we run into. Reducing heat loss, as we said, controlling unwanted heat gain during the summer, and controlling for infiltration of pollutants and maintaining that indoor air quality. Now, the mechanism by which air leakage occurs, there's several. One of them is wind loads. Wind can cause infiltration and exfiltration out of your building envelope. We have something called a stack effect, which is basically warm air rising, which is more of an issue when we look at high rises. And we can also have heat loss or air leakage due to mechanical HVAC interaction. So if we have a pressurized building, then we can have leaks through our building envelope as well. These are some photos of the issues that can happen due to unwanted air leakage. You can see on the top left, we have the underside of a roof in a roof attic space. What happens is warm air escaping from the building below escapes into the attic space, condenses on the underside of the roof, and eventually rots out the wood components there. If it's cold enough, it can cause frost formation. So significant durability issues. We can see that in walls as well when we have moist air condensing on brick causing fluorescence, or in precast, we can have significant ice formation that can cause delaminations and significant safety issues. So there are other things to worry about when it comes to air leakage, not just the heat loss, but that is our focus today. So going back to the idea of building as a system, we need to take into account the performance of the building envelope thermally when we look at the performance of our mechanical systems. The insulation and air tightness of the envelope can only do so much. In our climate, we still need mechanical systems to provide heating or cooling, but the amount of heating or cooling needed is dependent on the performance of our envelope. This is the idea behind the building as a system. And especially when we look at retrofits, increasing the performance of your envelope can allow you to use cheaper or more efficient mechanical system because they don't have to condition the air as much. This is poorly understood still, unfortunately. FCM shared some decarbonization study reports that municipalities often use, and we saw the envelope is barely mentioned in a lot of these, or sometimes not considered at all. So this is one of the critical items to take away today is when you ask for a decarbonization or a GHG reduction study for your building, make sure they're taking the building envelope into account because it's a significant item that impacts your energy performance.
I should add, Christian, that years ago I was exposed to a presentation by an architect of 47 slides of what happens when you add insulation to a building while respecting the airflow and the equilibrium that exists within the envelope itself. And a lot of the slides you had previously about the moisture. So, I mean, not only do we have to focus on the envelope as a system, but we have to think about the interaction between insulation and airflow and moisture and all those things. So it is a very complex issue, really, although it seems simple enough when you look at it in a picture like this. So
that's right. And Stephen, I think there's some there might be some questions in the chat. I can't see the chat.
Yeah, I'm monitoring those. So
okay,
yeah, so,
great.
Yeah, perfect.
Okay, so as we saw, the performance of the insulation in your walls can depend on the overall envelope design and construction. Thermal bridging through the studs has a significant effect. If you have, say, an R20 insulation in a steel stud wall, the studs will reduce the effectiveness of the wall by 50% easily. Other elements that could reduce the performance include improper installation of the insulation, or penetrations going through the wall that cause even more thermal bridging effects. So oftentimes what we see in new construction design, the architect will specify, I want, say, R22 insulation in this wall. But when we see how the wall is actually being built, if it's built like the photo on the left, you'd be lucky to get R5 out of that wall because of all that thermal bridging happening through the studs. Thermal bridging also happens through other elements in the building, especially for residential buildings. We look at balconies being a huge thermal bridge, and you can see that in the thermography scan at the bottom right there. The slabs are just glowing with heat, and that's because there's no insulation stopping the heat loss through the slabs. And that's a significant issue when we look at those high-rise residential buildings. And just one more note on thermal bridging, you can see some section views of why we have heat loss through the slabs, right? There's no insulation stopping it. Similarly, at the studs on the bottom left, you can see there can be significant heat loss and cause this issue called ghosting, where in the wintertime, the surface of the wall can get so cold that it picks up more dirt than the rest of the wall, and the studs just telegraph through the walls and cause these aesthetic issues as well as performance issues. And finally, on the top right, these are some section views of the transition between a wall and a window. This is another type of thermal bridge where two building envelope elements don't line up properly in terms of their thermal plane, where the insulation is in those elements, and that can cause these what we call flanking effects. So at the perimeter of the window, at the head, at the side, and at the bottom at the sill, if that window isn't lined up well with the insulation at the adjacent walls, we can have a lot of heat loss through the perimeter. Again, that principle of the energy will take the path of least resistance. I seem to have lost control of the slides. Okay, there we go. So windows are a very important part of our building envelope. They provide lighting and create a connection for the occupants to the outdoors, but they're also the weakest point of our building envelope in terms of thermal performance. Glass and metal are just not good insulating materials. We've figured out how to make better windows by adding more panes of glass and hermetically sealing them together using fancy inert gases in those cavities to reduce the conduction heat losses, using low emissivity coatings on the glass panes that reduce the radiation losses or gains. And when we look at retrofit projects, the windows are often the low-hanging fruit when we look at retrofitting buildings, because they are often, decades-old window systems just don't have very good thermal performance, and we can double or triple their performance with common modern systems. Doors similarly have our values that we need to take into account, though it's more important to look at, when you look at doors, look at the air tightness, make sure that they're well sealed, because air leakage is the main cause of heat loss through doors. Air leakage can be quantified by using these blower door tests. Sorry about that. Basically, we hook up big fans to the doorways and we pressurize or depressurize the building. We see how much airflow is flowing through them, and we can take that value and punch it into the energy model and see how much energy loss we have throughout the year because of these air leakages. It can also help us identify where the air is leaking from by using different techniques like thermographic scans or smoke machines, smoke pencils, things like that.
Yeah, Kristen, I know a lot of people say, well, we use those on residential applications, but you can't really use them on commercial. But they have been used on commercial. I once saw a 12-story condo. They used 6 blower door fans, and it worked. And you can also, in some cases, use the HVAC system, depending on the situation, to create the pressure to create the measurement too. So these techniques can work on much larger buildings and probably need to be done in order to understand really what the infiltration, exfiltration issues are.
Definitely. And some building codes and municipalities are requiring whole building air tightness testing for all new construction, such as Vancouver. If you're building even a high-rise building, it needs to be fully air tightness tested. Now, there are ways with really tall buildings to do a zoned test so that you're not pressurizing the whole building. That's a little bit outside of the scope of this presentation, but just so that you know that there are a lot of different ways that we can quantify for air leakage. So with all this knowledge, what have we done? We've built towers made out of metal and glass. So these towers have an overall R value of around R3 or R4, which turns out to be the same R value that a hut made out of mud would have. So have we really made much progress? But architects know this, builders know this. There are just other market forces that account for this type of construction. People like having large windows. Glass is a relatively cheap building material, but things are starting to change with modern building and energy codes becoming more stringent and requiring building envelope specific performance. Higher tiers of the Toronto Green Standard or the BC Step Code, for example, will require such performance that these glass towers really won't be possible. They just can't provide enough thermal performance, no matter how many panes of glass you use.
So what you're saying, Christian, is we know how to do it. We just have to now create the will in our organizations to actually do it and use the technology we understand.
That's right. And legislation and building codes are helping with that. So we see a lot of these designs changing. As I said, I work a lot with new construction, and there's a lot more pressure on making sure that our window to wall ratios are sufficient to allow for a whole building thermal performance that's required by code. How am I doing on time? Just wanted to check in. Stephen, you're muted.
About another 20 minutes, Christian. So yeah,
Okay,
it's getting
perfect.
tight.
Okay, I'll quickly go through this section so we can actually look at examples at the end. So one way we can account for heat loss is through thermal imaging. That's one of the tools we use. It can show where air leakage tends to happen, where we have thermal bridging, where window panes might have failed, where we have. It also helps with other durability issues, such as roof leaks and so on. I think we have some images of those. So in this example, you can see that on the image on the right, the purple pane of glass has failed. So their seal between the two panes of glass has failed, and there is air from the inside or outside coming into that pane of glass, which reduces the thermal performance. We have, in this example, one of the windows, one level of the windows has been replaced and the other one hasn't. This is taken from outside in the winter, so I don't know if you can tell, it's the bottom one that has been replaced. It's allowing all the heat from the inside to escape, and that's why it's glowing red hot in the image. As I said, these thermography scans can allow us to pinpoint some durability issues, some roof leaks. You can see that highlighted here. This may also be due to air leakage at the truss ends coming from inside the building. On flat roofs, it's commonly used where if we have a leak through the waterproofing membrane, the insulation will get wet. That insulation will stay warm even overnight. So if we go at night, we do a thermography scan, you'll see highlighted areas of insulation that where the roofing membrane might have failed. And then it also helps with air leakage, pinpointing where we need to do a possible air tightness retrofit. In this commercial building, we pressurize the inside of the tower just by using the HVAC system, as Stephen mentioned, we can do. And you can see a lot of air leakage happening through the panel joints of this precast building. Now quickly, thermal bridging. There are ways to calculate for your thermal bridging R value. You can see where the thermal bridges tend to happen at the base of the wall, at the perimeter of the windows, at any slab interfaces, wall to roof interfaces, and so on. These all are calculated together to create an effective R value. If you are curious, you can look at these references on how that calculation is actually done. BC Housing and BC Hydro have done a lot of work in this space, so you can check that out. And just in summary, the thermography scans help show where heat conduction and air leakage can happen. It can show us issues with the insulation and the roof, also in the walls. In windows, it can show us where window panes might have failed, and generally where air leakage tends to happen in the building envelope.
And in this structure, that was water leakage into the brick, and that was also a moisture issue too. So.
Okay, so this is the meat of the presentation, I would say. This is where we want to show some examples of projects we've recently done at WSP. As I said, a lot of decarbonization studies don't take into account building envelope, so we want to show how we approach that for our studies. At first, we need to consider the building as and the building's life cycle to try to identify when these retrofit projects can occur. And the point is here, we need to plan early, because as problems arise, building owners tend to restore or renew facade components that need immediate attention, like leaks, cracks, or maybe safety issues. But we need to zoom out and look at the bigger picture. What's a more efficient and effective way to maintain your building enclosure while meeting the overall needs of the building, including those for energy performance, or if your municipality has an energy target, we need to consider the whole building life cycle. This is just an example of a building that was built in the 70s. A lot of our building stock was built in 70s and 80s, especially for commercial buildings. And the point of this slide is to try to focus on when we can run these holistic large retrofit projects. So for a building of this age, you know, in the 90s would have been a good time to replace the HVAC and building envelope systems, because that's sort of the life cycle that we see with these components. Most of the time this wasn't done, and the HVAC system was replaced with something similar or slightly better. But now that we're seeing those systems needing full replacement as well, and that can be paired up with other facade components like curtain walls, which tend to have about a 40-50 year lifespan, and make sure that we are, again, thinking of the building as a system, reducing loads, and designing our mechanical system to meet those reduced loads. So at WSP, we've been involved with every stage of this type of project. Today, we're talking about decarbonization studies, but we also have a significant number of buildings moving on to the execution phase, where we're actually doing these large retrofit projects that include window replacement, overcladding, roof replacement, in terms of building envelope, and then the mechanical systems are also being retrofitted and improved, renewable energy also being considered. So we'll look at some of those next. But in general, these are some insights that we've gathered from our work thus far. Number one, there are no silver bullets. every building is unique, and we have to rely on good building science and planning to make sure these projects happen in the short term to meet our long-term energy goals. Major enclosure upgrades typically occur once every 20 years. That's just a rough estimate, but that's just to say that we need to make sure that, okay, I'm getting a 15-minute warning. That's great. We need to make sure that those projects are lined up with the mechanical HVAC upgrades. Set minimum targets, use long-term analysis. Simple payback period analysis for these projects sometimes are not beneficial because they are large investments. At the same time, we need to set minimum energy targets because there are many different ways that we can meet those reduced energy goals. And we need to explore every option, aligning with incentives, funding, and financing, prioritizing portfolio or neighborhood scale action, bundling projects together as much as possible can improve that economies of scale, and iterative analysis and planning. Like I said, the building as a system requires us to think of reducing loads first and then seeing what mechanical systems we can use. We might be able to use smaller systems, more efficient ones. So that should be an iterative process.
So Christian, one of the things I'll just mention to folks, and the folks from SEM can put a link to this, but back in January, I did a seminar for the SEM conference in Ottawa on life cycle costing. So looking at life cycle costing, you said simple payback isn't a good measure. It's not. But life cycle costing, where you look at the lowest life cycle cost over the life cycle of the building, a very good way to incorporate building envelope into a financial analysis. So I'll let somebody from SEM post a link to that recording. I'm pretty sure it's online. So back to you.
Perfect. So what does the actual process look like for these projects? Typically, we start by establishing the existing systems and the baseline performance of the building. Then the team includes specialists from different departments to collaborate and develop different measures or improvements to each system. And then the energy modeling team packages those into different options to meet different levels of energy or carbon performance. So in a multi-unit residential example, we often look at insulating the walls from the inside or improving the R value from the outside through recladding or overcladding. For HVAC systems, that usually looks, the team will evaluate different systems and potentially fuel switching to alternate systems with improved efficiency, and looking at renewable power such as PV or geothermal. So in this case, we've seen, we established different improvement levels. So depending on the wall construction, we can possibly do something from the inside. Oftentimes it includes recladding or overcladding the building walls with additional insulation. And then level 3 performance would be even more insulation that requires some more fancy support systems for the cladding. For the roofs, we typically look at increasing the insulation on the roof. There are other consequences of that. We have to look at what it does to the parapets, how high the parapets are, if there's access to the roofs, if there's mechanical units up there, that might all need to be addressed. And then with windows, as I said, windows are a low-hanging fruit. Oftentimes, just using a typical modern window will improve the R value significantly, but we can look at high-performance systems using triple glazing, using argon or krypton gas in the glazing units, using different framing materials like fiberglass or longer thermal breaks in your aluminum window systems.
So Christian, there are a few questions here with respect to thermal bridging. I know we've got a bit of time at the end for the question and answer, but I think it's relevant to this discussion here. So one is, there's two of them. What is the average heat loss through thermal bridging of wood studs? Is it significantly less than metal studs? And the other question related to that, are wood studs used to reduce thermal bridging, or is wood not a good material? So, and I think the final question is, in a retrofit scenario, what is the best way of identifying and eliminating thermal bridging, particularly if there aren't good drawings of the existing envelope? So I know those questions are kind of all related together to bridging, so maybe you can address that as a bundle.
Yeah, wood stud walls are better than steel stud. Steel stud is very, very highly conductive material. So where a steel stud wall might reduce the cavity insulation value by half, a wood stud wall might reduce it by 25%. When we look at retrofit projects, there's oftentimes not a way to replace the wall structural elements like the studs. So we need to look at how we can insulate inside of that or outside of it. But yeah, wood it's got an R value of around R1 per inch. So much better than steel, which is 0.0001. And what
In
was the
terms of
last question?
the last question is, in a retrofit scenario, what's the best way of identifying or eliminating thermal bridging? I think that comes back to the overcladding and the recladding, either outside or possibly inside. Continuous insulation.
Make your insulation as continuous as possible and reduce thermal bridging. On the inside, there are ways you can build another layer of wall inside of your existing wall. It's not very common to see that. Most commonly, we insulate from the outside, and we use thermally broken cladding systems that don't just hook up your studs with another piece of metal to the cladding. We use different materials that are thermally broken so that we don't have that thermal bridging issue. And you can look at the thickness of the exterior insulation will provide different R values, of course. Our 2 inches, 4 inches, 6 inches are often seen. More than that, you have sort of, you drop off in R value, and you don't really get much more bang for your buck outside of our 6 inches or 8 inches.
That's great. So we knocked up a few questions there. I just want to get those done because they're kind of relevant. Perfect. And save a bit of time at the end. Go for it.
Appreciate that. Okay, here are some examples of some recent projects. So sometimes we see facades that are deteriorated and need significant interventions in the short term. For these buildings, mechanical retrofits were also required. So given the level of repairs, the client wanted us to see what possible upgrades we can do to achieve net zero performance. But because the enclosure, the facade was in a state of disrepair and it was becoming an urgent issue, we were able to squeeze in a preliminary red screen analysis, which Stephen will talk a bit more about, to help with the decision-making for the envelope upgrades. With a red screen model, we can see, okay, if we use 4 inches of insulation and we upgrade the mechanical systems this way, what is the total energy reduction? So with that analysis, we were able to pinpoint, okay, we actually need 6 inches of insulation here. We need a window that has an R value of so-and-so, and maybe the roof we can leave aside. So that is the benefit of doing a red screen analysis for these two projects. Had the envelope repairs happened without the modeling, it would have been a lot more difficult to achieve those net zero goals. And in the end result in a less optimized design.
Christian, that kind of relates to questions that are out there, which I'll address when I get to the red screen session.
Okay.
But about the financials and using red screen to really get a good picture on what's happening. So I will come back to those questions.
Perfect. These are just some renderings of the typical overcladding solutions that we look at. So on the top left, you can see an eaves overcladding option. So that is the brick has a membrane applied to it, which has other benefits as well. All those brick repairs that you're doing every year no longer need to be done. So that needs to be considered in the financial calculus as well. And then we have our expanded polystyrene and finishing coats on the outside. For that example, we can also do a metal overclad project, and you can see there we have different insulation, this mineral wool, and the metal vertical girts are supported on thermally broken clips. So those clips have thermal bridging issues, or they account for some thermal bridging losses, but they're not as bad as just having an aluminum girt tying back to the brick, for example. So that's one way we can reduce those thermal bridging issues. And at the bottom, those are some high performance window systems. You can see the aluminum is separated by that black polymer that's called a thermal break, and in these systems the thermal break is large enough that we can get a really good R value from these window systems, and they're also the cavities are fully insulated as well. So once we look at all the elements of the building envelope and how we can potentially upgrade them, we list them in the study. Then the energy modeling team bundles them together with the mechanical and possibly renewable projects that we can undertake, and we can get we can calculate the total GHG emission reduction, or the energy use reduction. And as I said, there's different ways to get to the same goal. So these are 3 different options that we presented for this project. Option 1 was using EnerFit principles, so the passive house retrofit guides, and it resulted in a very much more thermally efficient building. We also looked at a hybrid approach and a least cost approach, and you can see at the bottom in the table what the GHG emission reduction was and the energy use reduction as well, compared to the owner's RFP target. So as I said, there's different ways to achieve the same goal. We just need to take a building as a system approach to all these projects.
That's great, Christian, because that's a great segue into the tool RedScreen Expert. Some of you may have seen it, some of you may have not have heard of it, some of you may have heard of it. You could all tomorrow go and download a viewer version of RedScreen Expert from www.redscreen.net. We probably should have put that on a slide somewhere. We didn't, but www.redscreen.net, and you can download a free copy. Now, you don't have to license it, and you can try the things out that I'm going to show you here just in the free version. You won't be able to save things in the free version, but you'll certainly be able to give it a try. So what I'm going to do is introduce you to what's called the Virtual Energy Analyzer. So slide 46. So the next slide there, Christian, talks about municipal building archetypes. An archetype is designed or is defined as something that's very typical of other things. So RedScreen has actually built a whole series of typical models, very typical models of different kinds of buildings. One of the questions asked in the Q&A there was, what about retrofit of building envelope measures in different geographical or different climatic locations? Well, these archetypes are designed to do just that. So you can take an archetype, say, of a fire hall. I've got one shown there, and it's a typical building, looks like a fire hall. It's got a building envelope attached to it. It's got HVAC systems, and you can say, okay, put that building in Ottawa, put that building in BC, put that building in St. John's, put that building in Saskatoon. You could literally pick it up on the map and move it and see the results, right? And I'll show you in a second the kind of results you get out of it. So the archetypes are very useful, allowing you to do some what-if type of analysis. They're a predefined building. If you've got somebody who's a building modeler like Christian, or maybe you could have somebody in a municipality that could use RedScreen to build up your own models. But this is kind of a head start thing. Okay, what if I have a building like a fire hall, a community center? What might I do to take that building to a 40 to 50% reduction in energy, or an 80 to 90% reduction in greenhouse gas emissions? So RedScreen's Virtual Energy Analyzer with its archetypes is the tool you can kind of go and play with. It's kind of like a game, but it's very real. Next slide. We just look at an arena archetype. So in the arena archetype, we have all the different parts of the building detailed, the energy used in each of those different types of or parts of the building. But on the right-hand side, somebody asked about the distribution of the contribution of the different systems in a building and maybe the savings. Well, that's a pie chart of all of the savings opportunities in that archetype, which is built into RedScreen. So all you got to do is open up, because I think this is the arena archetype, and it's the 30 to 40% one. So it's not a full net zero ready archetype, but basically it's a pretty aggressive archetype. And that's how the savings break down between the space heating and the heat recovery and so on. But you can see space heating, which is largely building envelope, is a large component of the opportunity in that building. Going a little further on the next slide, we can actually see some more that you get out of this. So if you want to know the carbon contribution, this is another archetype. This is actually a fire station. You get the pie chart of where all the heat losses are, where the savings are, but you also get that nice little bar chart which shows you 56% reduction in CO2. You move that building to Alberta, you move it to St. John's, you move it to Bank, wherever you put it, it's going to tell you that same number. So you can kind of play the what if I do this. And what if I change? Maybe you want to get more aggressive with the insulation in the roof. Maybe you want to put a higher performance window in, so you can actually go. So in the next slide here, we'll see the building envelope model, and that's where you can actually go in and change the values, the components of that building. That's the building envelope model for one of those archetypes. All right, it's complicated, but it's not as complicated as a lot of other models. The beauty of this tool is it gets you to an answer much quicker than some of the other more detailed simulations. So RedScreen is becoming quite widely known for that purpose. So have a look at it, www.redscreen.net, take a look. So I'm just going to finish off very quickly here, like literally within 2 or 3 minutes. The order of these things is important. As Christian talked about, and when he was talking, he kind of alluded to the fact that the size of your HVAC system is determined by how much heat loss you have from the building. So to me, it's very important to consider things like air sealing, insulation and ventilation, windows, all those envelope measures, because they all impact your heating and cooling systems. And if you're going to change your heating and cooling systems to things like heat pumps, either a ground source and air source, you want to know what the size you're going to need is. And you need to know pretty closely, because you can oversize a furnace, like a gas furnace, by 100%. It might cost you 20% more. You double the size of a heat pump, it's probably going to cost you close to double the price. And so you need to know that sizing properly. And to get to that most cost-effective and efficient building and lowest carbon building, you've got to treat these things as a system. This is a graphic that comes from Green Building Advisor. You can go and look. There's some good stuff on that website. Talk about the pyramid, right? But the order. But the idea here is work your way towards those renewable options. And envelope is definitely part of it, right? Which contributes to the requirement for renewables, but also the requirements for heating and cooling. So there is an order, and it's important. Next slide. There's some good guidance around this. So there's a guide called the Major Energy Retrofit Guidelines, available from Natural Resources Canada at that website. And within that guide, on the next slide, we'll see that they talk about this order. So existing building commissioning, lighting upgrades, and it's a fancy term, supplemental load reduction. But inside that is building envelopes. If you go in there and look at it, it says these are all things you got to do, because the next step in that major retrofit is the air or water system distributions and upgrades to those, and then the heating cooling equipment itself is where you do your heat pumps and your renewables beyond that. So firmly in the middle of the critical path is the building envelope. And you alluded to the fact oftentimes we see these studies that don't actually do good consideration, do their diligence around the building envelope. Very important. So on that note, just a few things to keep in mind. I'm not going to read these. I think the key thing is to consider the system, the building holistically, consider all the interactions. And to the name of this webinar to begin with, you're not only going to have a building that's more energy efficient. If you pay attention to the building envelope, you're going to have one that's more comfortable, and to Christian's point throughout, one that's more durable, right? And resilient in that sense, right? To moisture and all those types of things. So just keep in mind, that even a small change can make a big difference in this business, right? And big things come out of small actions, one step at a time. So on that note, I'm going to turn it back to Corey. Who's online there? There we go. Yes, Corey, good.
Yeah, we have a couple minutes here. We can try to get to some more of the questions. I'll let you choose which one, and we'll just save a couple minutes at the end, and I'll run a quick poll of the session.
Yeah, so there's a good question there. Joe can ask, so how is the accuracy of RedScreen in estimating building envelope energy savings compared to other software, eQuest, IES, Energy Plus? The accuracy of any simulation or modeling tool is as good as the person using it, right? So Kristen, I'm going to kind of flip back to you, because I have worked with your folks and they do use these other tools, but there's also a cost issue too. You can spend a lot of time on a detailed simulation program, and come up with an answer, which may not be sort of markedly better than what you get out of red screen, but it really comes down to the skill of the simulator or the modeler. One key principle that I use to ensure I would say better accuracy is to reconcile your building's modeled energy back to what you consumed. There's a lot of energy audits that are done out there that never make that comparison. Okay, here's what my model says. This is what I'm going to base my savings on. But does its prediction compare to historical consumption? If you do that one thing, it makes a huge difference to the accuracy. It's hard to answer the question about accuracy, but the best practices contribute to accuracy. What are your typical cutoff points for building retrofit payback? I mean, Kristen, I think Christian don't like to use simple payback. We would, really just, if you've got to do something to a building, you've got to take the least cost path. That's where life cycle costing come in. Do you want to speak to that one, Christian?
Yeah, like we said, there's a lot of low-hanging fruit that we need to tackle first. Typical cutoff points, and I don't know if there's a typical point. Every client is different for us, and I'm the building envelope specialist, so I tend to leave that up to the other folks. But just on the building envelope side, window retrofits tend to have decent payback because of their life cycle. They need to be replaced anyway. So the additional cost of using a high performance system usually does pay back in the energy performance of it.
I'm just going to add one thing back to the question about accuracy. There is a set of tests called the Building Energy Simulation Test, BEST test. Red Screen has performed very well in those tests. If you go look at BEST test building simulation, that kind of answers the question about accuracy. It's hard to answer that one, but that's a reasonably good